Okay, so with all this discussion about broadening and all that, let's finally get to the light source that we use for atomic absorption spectroscopy, and now we will understand why it's designed the way it is. Okay, so this is a hollow cathode lamp. This is a figure showing sort of what it looks like. So we don't have a traditional light source like a tungsten filament lamp or something like that. Instead, we're still using electrical discharge. We have an anode here, which is, this is something that's going to produce electrons. Come on. Oh man. All right, let's try this again. This is going to produce electrons, and these electrons are going to go through this this gap here. So this is not directly connected, and they're going to strike this hollow cathode. Right, this is where our reduction is happening. So, right, this is our negatively charged side. Oh, sorry. This is our positively charged side or negatively charged side. So our electrons are going to bombard our hollow cathode, and the cathode is made of the material we're trying to measure. So made of material we're measuring. What happens is as these electrons strike the metal that we're... My computer's lagging a little bit. So electrons are going to strike the metal, and that's going to produce excited metal atoms. Generally, atomic absorption is looking at metals, though you can look at other things too. And that metal is then going to emit a photon. Now, what's nice about this is it will emit photons at the same energy level difference at which your sample is going to absorb. And so what's great about hollow cathode lamps is that it produces the exact wavelengths of light that you need. Because you are producing the light with the exact same thing that your sample is made of, that your analyte. So I think that's really clever about hollow cathode lamps, is that you use what you're trying to measure to produce exactly what you need from what you're trying to measure. So the whole point of this electrical discharge is that we're producing excited atoms that then emit, which is exactly what we're trying to observe in the atomic absorption experiment. We're trying to observe those same atoms. Now, how does some other details about this that are relevant? We have a low pressure of gas inside of here, of some sort of inert gas. So something like 1 to 5 torr, whereas atmospheric pressure is about 760 torr, of something like neon or argon, something that won't react, right? We have a noble gas in there. And then, and this whole thing is occurring at a much lower temperature than our flame. Now, the reason that we keep things at a low pressure and that this is happening at a low temperature is that leads to, we have decreased Doppler broadening because our temperature is much lower than it is in the flame. And we have decreased pressure broadening because the pressure is also significantly lower because we have this reduced pressure environment. What that means is that we have a light source where the width of the light that's produced is significantly narrower than the width of the absorption peaks, which means that Beer's law is going to apply. And that's what's shown in this figure here. So the blue here in the middle, this is our light source. This is our light from our hollow cathode lamp. And we can see because of the the decreased Doppler and pressure broadening, the width of that absorption line, width of that emission line is much narrower than the width of the absorption line here. And so Beer's law is going to apply. Now, if we tried to do this with a monochromator, the monochromator bandwidth is like 100 times bigger than these atomic lines. And we'd have no hope of having something narrow enough for Beer's law to actually apply here. But with a hollow cathode lamp, we do. Because it's designed to work at a lower temperature and lower pressure than our sample, it means we can get light that is much narrower. It's much closer to the natural line width. It's not at the natural line width, but it's much closer to the natural line width, or the lifetime broadening, than than what's happening inside of our flame or ICP. And so, yeah, that's the idea behind a hollow cathode lamp. So you have to have a different hollow cathode lamp for the different types of things you're trying to observe. So if you're trying to observe a specific metal, you need that metal inside of the hollow cathode lamp. So unlike UV vis spectrometers where you have a broadband light source, you instead get very specific wavelengths here that are directly related to the wavelengths of the atom that you're trying to measure, which is an advantage and a disadvantage. The advantage is that you get the exact colors of light that you need. The disadvantage is that you have to have a different lamp for the different metals that you're observing. Now, what you can do, and for example, the one that we have downstairs are you can have multiple lamps installed in one spectrometer, which can help you measure multiple things without having to like change everything out every time. So, okay, so that's it for our light sources, and from here we're going to talk about a couple of other things in terms of looking at multiple elements at the same time, background correction, and types of interference in atomic spectroscopy.